Okay, welcome back to this lecture on introductory quantum mechanics for quantitative and computational biologists. We have spent a lecture recently to sort of summarize the main features that have emerged in our analysis of the breakdown of classical description at the microscopic scale, which we would like to incorporate into the new theory that needs to be constructed in order to account for this new phenomenology. And we came to the conclusion that propagation of particles occurs through a wave-like behavior, but that the detected properties of particles are that of a particle in that, of a quantum particle, are that of a classical particle, which in turn we interpreted in the fact that we need to introduce, the concept of a function that describes the evolution of probability amplitude, therefore responsible for interference pattern, and we call that the wave function psi of x and t. And remember, for simplicity, I'm using a one-dimensional description here. We might upgrade this to higher dimension, allowing x, y, and z component and multiple particles at some points. But for the moment, we are sticking to the simplest possible situation. And we call this the wave function. And we came to the conclusion that the probability of detecting the particle at position x at time t is obtained from the wave function through a square modulus, just as it happens with amplitude going into intensity for electromagnetic waves. So that's the first statement. We look at the interference pattern of the electron on the screen, and we try to account for that in the most intuitive way, that is, relying on what we know waves already do. But since we also said that a particle hits the screen, and once it's detected, the properties that are detected are that of a classical particle, we also want something that eventually for an electron will give me a kinetic energy, which is the typical kinetic energy of a particle. We call that fact number 1 in a previous lecture. We can think of this as a result of an experiment through calorimetry type of setups. So the third thing we want to sort of account for is that since we know from the study of photons that the electrons, the energy of the photon is somewhat proportional to the frequency of the pulsation through the Planck's constants. Since this is true for photon, we want to develop a theory which generalizes that to any quantum particle. So this is a bit of a bold guess at this moment. And the fact that I'm presenting this as a fact, which actually a little bit improper, it's the result of a number of experiments that ultimately, led to conclude that this is true. So in historical terms, it's by no means clear that people were assuming these facts and then arrived to the Schrödinger equation. I'm presenting that in those facts in this order for the pedagogical purposes, in order to motivate ourselves into the transition from classical world to quantum world, going from particle to Schrödinger equations for wave functions. So there's nothing historic here. Things didn't evolve the way I present them. It's just a interesting way of looking at how some evidence was ultimately collected, how you can place them in the right order to inspire you to arrive to the Schrödinger equation without being Schrödinger itself. So the one thing we came to the conclusion is the part that electrons propagate as waves. And we want to satisfy these two constraints that I just listed here. So the simplest thing we tried last lecture was the standard wave equation. The same equation that is obeyed by acoustic wave, but also by electromagnetic wave. And since this particular properties was obeyed by electromagnetic waves and photons, and we transferred this property to the electrons, why not transferring the same equations to the electron. I mean, it sounds a feasible thing to be doing. So what we tried to see is whether we could sort of apply an equation in the form, a wave equation in the form 1 over velocity square, which we can write as p square over m square, second derivative with respect to time of the wave function is equal, or if you want, the negative of second derivative with respect to space of the wave function is equal to 0. So what we're trying to do was to sort of, this was a guess, to follow the implication of this guess. And what we arrived after some very basic calculation is to the conclusion that the energy square of a particle was actually proportional to the momentum square of a particle. At least for a plane wave, we used a model in which, if you remember, the wave function was supposed to be something like this, which is called a plane wave. And since this object P has a dimension of momentum, we were led to thinking, well, let it be the momentum of the particle. Now, if you take these ansatz and you say, my electron is wave function is well described by this plane wave, as it would be an electromagnetic wave propagating, and you channel this equation into the standard wave equation, which is what electromagnetic wave obey, you get a relationship between the energy and the momentum that is not that of a particle, but is that of an electromagnetic radiation. Because for electromagnetic radiation, the energy is proportional to the momentum through the velocity of light. On the other hand, we want the energy to be proportional to the momentum square for an electron. So, no big surprise. If you assume the electron behaves exactly like the electromagnetic radiation, we're going to have as an outcome the fact that the electron behaves like an electromagnetic radiation, meaning that its dispersion relationship between energy and momentum will be the same of an electromagnetic wave, which is, of course, something we do not want because we know it's not true. So that's where we stopped last time, and we said, okay, fine. We are not able to, write down the equation for the electron. But I concluded last lecture with the observation that maybe from this failure we can get the right inspiration that correct our initial guess and get an equation that is not contradictory in terms like the present one. And in fact, what we're going to be doing now is precisely this. It's sort of reanalyzing. So, see, what we want is something like this. Because we know that the energy is actually P squared over 2m, right? But what we get is something like this, extra 2. So the question is, where does the extra 2 comes from, extra energy comes from, and how to get rid of it? Now, if you go back and look at our plane wave gas of psi, so this part simply is accounting from the fact that the pulsation, or omega times h bar, is the energy. And we want to leave that as it is because we know that that's a property we want to respect in our theory, to fulfill. And then, of course, the second part here, p dot x, which I'll write in one dimension, simply comes from the fact that we want this to be a propagating wave in the direction set by the momentum, to the velocity proportional to the momentum, so on and so forth. Okay, so there's not much freedom. This is my ansatz for the solution, and I want to keep this. So what I'm going to do is to notice that the problem arises anytime I differentiate with respect to x, I get a power of momentum. So the p squared in my dispersion relationship comes from the fact that I differentiated twice with respect to x. Now, the e square in the relationship that I found came from the fact that I differentiated twice with respect to time. Now, I don't want two powers of energy. I want a single power of energy because I want the energy to be proportional to p squared, like in E equals p squared over 2m. So why don't I just take a single time derivative? Let's see what happens. Well, if I take a single time derivative of this function, so let me clear the board and say, okay, again, here is my answer, and now I'm writing this in a slightly different notation, but I think we all agree we're talking about the same thing. Now I'm going to take a single time derivative of psi. And this is going to be a I over h bar omega, and then psi of x and t. I'm pulling down this factor here. And then I'm going to take the fact that omega over, sorry, I'm making a mistake here. This is actually, and then I'm going to take the second derivative of x. And I'm going to drop I'm going to drop a -1 from the I square. I'm going to drop a h bar squared. And I'm going to drop a p squared times psi of x and t. So now, clearly, I want to combine these two terms to form an equation that is fulfilled if E is equal to p squared over 2m. So basically what I'm going to do is I'm going to put here two constants, C1, and then I get d by dt plus a constant C2. Actually, let's put a negative, like in the wave equation, C2. It's completely arbitrary. You will just change the sign of psi of C2 times d squared by dx squared equal to 0, and of course both terms are applied to the wave function. And all I have to do is now to use the results that I just wrote about to determine what C1 and C2 are. Now, let's focus on this. First of all, let's look at this term here. This one. What I'm going to do, I'm going to replace it with this term here. Psi goes already on the way to here, so I don't need to copy it inside. I'm going to write I over h bar e. I should write also a, but a is going to appear the same also in there in the next term, and it's going to cancel out. So let me not even write it. Now let me look at the second term and use this second expression to replace this. So again, like I said, a is going to cancel out. Then I get a -1, which is on the plus here, 1 over h bar squared p squared. Now, I want this to be 0, which means that this argument in here, which I'm now circling in green, must vanish, because if this argument vanishes, then no matter what psi is, this is going to be 0. So we came to the conclusion that a good guess for our wave function equation is one in which C1 I over h bar e plus C2 1 over h bar p squared is equal to 0. Then, of course, there are two constants for one equation. You don't need that. So what I can actually do, well, you can do it many ways. One thing is clear, C1 must be an imaginary. So the first, and there's a square here, right? So the first thing we understand is that C1 must include an I and an H bar. Because the I must cancel the I that sits here, giving an overall minus sign, which will be used to cancel this. And then I have some redundancy. I can set C2 to 1 and then rescale C1 at my taste. So why don't, see, there are two constants, C1 and C2, and I don't really need two constants, right? I mean, after all, it's just one equation that I want to satisfy. So, I can call this first constant, I can call like C1 divided by C2, let me call it R, and this equation will become R, and then we get a 1 here. So once again, I know that R must be proportional to I divided by A squared, but that's not good enough. If I get just R is equal to I over A squared, I'm gonna get E squared is equal, E is equal to P squared, which is obviously not true. So what I need here is to divide here by 1 over 2n. So eventually, all it boils down to that my equation describing the wave with this equation will be the equation I'm looking for. So I can identify this with C1 if you want, and this with C2. Why? Because if I do this equation, if I assume this equation, I get two main outcome outside. First of all, I get a wave solution, which is what I want. And second, I get a solution. Once I apply this, assuming the plane wave solution, I will get that the energy of my electron will be p squared over 2m, assuming that the energy is proportional to the frequency. So I'll be able to satisfy all three requests that I asked I should satisfy. Now, the fact that I pulled outside a factor h bar here instead of having in the denominator is purely conventional. All it does is rescaling the definition of psi. So, in the previous equation, I had an h bar here and an h bar square on the side in the denominator. I just multiply everything by appropriate powers of h bar in order to get the h bar in numerator rather than the denominator, and I divide it by 2m. So once again, how did I come to this equation? Well, I was looking for coefficients to put in front of the time derivative, either two independent coefficients or a single coefficient, then you readjust things at the end. You can work either way, but the main point here is to put coefficients that ensures that you get 0 here if E is equal to square over 2m. And the choice that saves the day is the one that I reported in the equation here. So this equation relates a time derivative to a space derivative. But the physical interpretation of this equation is just transparent because basically what this second term of the equation is doing is to pulling down something like p squared 2m outside of the wave function. So what this equation is telling you is that if you take what this equation is telling you, if you take the Planck's constant, the Dirac constant multiplied by E and take the time derivative of the wave function, what you get out is basically related to the kinetic energy of the electron, multiplied by epsilon. Now, for a free particle, the idea is there's something, that allows you, based on this discussion we had, it's clear that there's something that basically relates this second derivative with respect to x with this specific combination to be basically a way to extracting the kinetic energy of my electron. So I get something like A times d by dt dot psi is equal to some mathematical operation, let's I call it H naught. And if I carry on this mathematical operation, what I basically get out is the kinetic energy. And what is the mathematical operation? Is taken twice the space derivative and take a negative sign, multiply by h bar and divided by twice that. So mathematically, it could be sort of confusing if you're not acquainted to what I'm doing. But what I'm trying to say is that we're trying to dig out some physics from this equation we wrote, and the conclusion we are getting is that this equation relates time derivative to a mathematical procedure to extract information about the kinetic energy. And we call the mathematical procedure, we look at this mathematical procedure, and what it actually is a differential operator. What is an operator? It's basically a mathematical object that takes a function and gives me in return another function. In particular, the gradient, the Laplacian, the rotor, they're all differential operators, as you have seen in the mathematical background classes. So what we arrive to the conclusion is for a free plane wave, the equation that has a good candidate to describe the motion of the electron is one in which you equate the time derivative times I, the Dirac's constants, applied to the wave function, so a time derivative operator, is equal to an operator H naught that describes basically the Laplacian in multiple dimensions, up to a factor h bar squared. Now this is it for a plane wave which only has kinetic energy. Now here goes the bold guess. What if the electron is actually interacting with, say, an electric field or a gravitational field or another electron or a proton or magnetic field? Then clearly it will not propagate. Its energy will not be just the kinetic energy. The energy of the electron will be the kinetic energy plus the potential energy of the electron. So here comes the bold guess. Since this is the kinetic energy, what happens if I switch on the potential energy? Well, I sum the potential energy to the kinetic energy. So here goes the final guess. That the equation that describes the motion of the electron, now relaxing the hypothesis that the electron is not interacting anymore, allowing the electron to interact, will be described by a new mathematical operator acting. Well, let me make explicit the dependency on the position. And the new mathematical operator, now see the naught in H naught has disappeared. because the note there was only to remind myself that I was excluding the possibility of having interaction. And the new operator H is basically something that has the interpretation of an energy, and it basically corresponds to a part that in multiple dimensions. Now I wrote the Laplacian square. Remember the Laplacian square is u squared by dx squared plus t squared by dy squared plus v squared by z squared. And since I have only x squared in one dimension, in multiple dimensions I have all three. But also now, since I'm considering interaction, I'm adding also the potential energy. So here I get an object, a function that has the same name as the Hamiltonian, because it's written over. And also the physical interpretation of the Hamiltonian. Given the state of a system, described by wave function, it pulls out the energy of that, just as much as the classical Hamiltonian. Remember, the classical Hamiltonian was the sum of kinetic and potential energy. This quantum Hamiltonian is again the sum of something that extracts the kinetic and add the potential energy to the particle. So based on this, we shall refer as this differential operator H as the quantum Hamiltonian. Cool. And this here is the heart of quantum mechanics, and is the well-known, infamous Schrödinger equation. It is one of the most famous and not to mention relevant equations in the history of physics and, dare I say, of mankind. We went from describing something classical and, resembling the behavior of, say, cannonballs, to the electrons, down to the microscopic world. We have an equation that we think is a good candidate to describe the microscopic world. Now, this discussion, I will never emphasize enough, is by no means a theoretical derivation of the Schrödinger equation. There are so many loopholes and things that we, how do we know that we can simply add kinetic energy and potential energy? There's no way I should add it. It's just I'm making an educated guess. Ultimately, I could have just, opened this lecture saying, so we need a wave function. This is the equation that people have discovered for the wave function. How come? Oh, they tried many others, and this was the only one to eventually survive. And that was as good answer as the one that I gave you here from the epistemological and ontological point of view. There was nothing more than what I just, guess the right function and eventually stick to the right function. Nevertheless, I think from the discussion that we had, it emerged the fact that this, in order to get something that resembles the right energy of a particle, you need to put the right differential operator. And eventually what you get is the time derivative of the wave function must be equal to something that extracts the mechanical energy from the wave function. And this something that extracts the mechanical energy, computes the mechanical energy given the wave function, is called the Hamiltonian. But since it's not the classical Hamiltonian we used to see, but it's the Hamiltonian that enters in quantum mechanics, it's called the quantum Hamiltonian. Okay? So this equation is the heart of most of mathematical description of quantum mechanical world, at least away from the relativistic regimes where particles begin to travel at the speed of light or nearby, where things change dramatically. As we know, because we know that photons do not obey this equation. The photons do obey an equation with a second time derivative, right? We've seen that already. So we arrived to write down the Schrodinger equation. And basically everything that will follow in condensed matter theory, every property of matter, the very existence of atoms, the very existence of molecules, the existence of the macromolecules of life, ourselves, everything concerns when matter gets together to form aggregated states or condensed states follows solely from this equation and a couple of more inputs we're going to put there to complete the discussion of quantum mechanics. So this is really, 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 really a cornerstone in science, not only in physics. Okay, so we have written an equation. We sort of understand where it comes from, but we have no idea how to use it to solve problems and determine the motion of particles. So you see, this equation is a very complicated equation. It involves partial derivative with respect to time and position. So this is called a partial differential equation, or a PDE. And PDEs are damn hard to solve. And basically, quite a lot of the rest of this course will be devoted at some point in figuring out how to solve this in practical problems. But the one thing I want to emphasize is what this equation is all about is the evolution of the wave function. Because it contains on the left-hand side the time derivative of the wave function. And it provides something on the right-hand side. So now I'm saying this because a bell should ring in your mind that since the hard equation of quantum mechanics is one in which I have time derivative on the left and something on the right, right? Let me write this. You may say, yes, it's time derivative. Where is the i's gone? Well, the i's gone here with h bar, right? So I don't need to worry. Now, this should look to your eyes very much like I have time derivative of the state on the left and something on the right. And remember, in classical mechanics, that something on the right was specified if you knew the classical Hamiltonian. And in quantum mechanics, something on the right is the something that sits on the right can be specified if you know the quantum Hamiltonian. So really, we are getting to the point, we're getting hints that this wave function here has something to do with the state of the system. In quantum mechanics. Because remember, the state of the system in classical mechanics was a point in phase space, and Hamilton's equation could have been written as time derivative of the phase space vector equals something given the Hamiltonian, and that's something where the Hamilton's equation. And in quantum mechanics, we have the time derivative of the wave function is equals something that can be determined knowing the Hamiltonian. So a hint comes through, which we will deepen later on in these lectures, that the wave function is something as close as it gets to the mathematical objects that defines the state of the system in quantum mechanics. So if I were to build a dictionary in what we did so far, we get classical mechanics, state, wave function. Time derivative of the state equals here something as a function of h. These are the Hamilton's equations. So let me write it as negative dh, sorry, plus dh by dp, and negative dh by dq. That's Hamilton's equations. And here I get partial derivative with respect to e I h bar of the wave function is equal to h of differential operator up to that. So once again, we are ready to go back to the double slit experiment and say, okay, fine, we have our gun, we have our double slit, and we have our board. And the idea is that the gun emits electrons, and electrons are described by waves with an amplitude psi of x of t. And the way this amplitude of waves propagates in space is well described by the Schrodinger equations. When the wave impacts a hole, it will pass through only in the two holes, so there will be two circular waves, and these two circular waves will interfere with each other, will add up with each other. Just as much as the wave on the ocean, we get the forthcoming and the backcoming, and they sum up in a linear way. So these two holes will interfere, will sum up, giving rise to different interference pattern. And when you compute the square modulus of the wave function here, you get a probability of observing the wave at the board, observing the electron, and this will be described well by the interference pattern. So that's the essence of the discussion we've had so far in this course. Now, the fact that we have uncertainty has sort of reflected itself in the fact that we no longer speak in terms of phase-space trajectories, but our essential state descriptor has a stochastic interpretation. The essence of quantum mechanics, what we use to describe the state of a system, is a wave function that is related to a probability. Hence, not something deterministic, but something really stochastic in the very nature. So the entire foundation of quantum mechanics is based on computing probability for the outcome of an experiment, which in this case is I measure the electron on the final board. So quantum mechanics is not about nature itself, but rather about predicting the outcomes of performing experiments on nature. It looks like a philosophical question, and in many ways it is, but it's a very deep and fundamental one. The difference between saying I have a physical theory that describes nature and I have a physical theory that describes the possible outcomes of measuring nature sets our ambition to an entirely different level, much lower. We give up being able to say how God, that it be a real belief or a philosophical sort of inspired discussion, how this God actually designed nature in terms of intelligent design. We are not trying to read God's mind, so to say. whether you believe or not in God. I mean, again, this is not a real theological statement here, it's just an analogy, right? We are not about understanding the code of nature. We are interested in understanding, being predictive about what happens if we measure nature. But if you think about it, can we really say anything else? So this is exactly what Einstein hated about quantum mechanics. God doesn't play dice. He was writing famously in a correspondence with Niels Bohr. God doesn't play dice. So our fundamental theory of nature cannot be a stochastic theory, which we only describe the possible outcome of the experiment. Yet, when we have a physical system interacting with nature, the only way you can learn about nature is by interacting with it, performing an experiment. So the point is that all we ever do is actually mediated by experiment. Vision is an experiment, is detecting photons. Hearing is an experiment, detecting acoustic waves. So there is no interface with nature whatsoever. There is no nature. There's no one if there is no physical interaction through experiment. So why should the theory that human beings develop using detecting lights and motions, the only notion of themselves and their world is about probing the environment? Why should the physical theory be about the environment itself? It can only be about the fact of interfacing yourself with the environment. So, although at the beginning it looks completely strange that the physical theory has gone as low as giving up telling something about nature, but only asking to predict the outcome of experimenting nature, if you think long enough, you might come to the same conclusion that that's basically the only thing that any system made of matter can say about an environment made of matter itself. Because matter can interact with matter through interactions, and that interaction, if done in a specific way, is called the experiment. So quantum mechanics just systematize this operation in a well-organized framework, mathematical framework, which we're going to further develop. But I really want you to think about how deep is this, because it's really a cornerstone in science, giving up natural philosophy and looking instead at science in an entirely different perspective. I mean, it shocked my mind, and I hope it's going to a little bit shake your mind too. Okay, I think I call it a little bit shorter lecture today because I don't want to start a new topic. It will be longer on the discussion, maybe on Wednesdays, we need more time. But I'd rather not enter a new topic at this level. I'd like to leave it there with this question and with final point to resonate in your mind. How far have we gone? Because our initial problem was completely practical, understanding what happens to an electron that goes through double slit. And the outcome of that analysis was enormously deep in terms of where we stand in the world. It led us to reconceive what it means to be doing science and to be exploring nature. And led us to believe that between measuring nature and thinking about nature is very deep, and somehow it cannot be broken. You can never disentangle theory from the experiment, to the point that your theory is only about the outcome of an experiment, not about the theory itself, about nature itself. Strongly anti-Einstein-like interpretation of nature. This goes under the name of the well-famous Copenhagen interpretation. We will discuss this more and more in depth in the future. Okay, I think it's a good time to stop and think about it.